It is February 16th. It's February 16th, and we're going to have our next, this is our next libembeddedhal meeting. I'm Khalil Stell, and I'm going to go over it. Still almost done with those CAN bus drivers. We'll get there at some point. I got one little, got some documentation we got to fix up before we can merge it in. Today I'm going to go over unit testing and the code create process just a little bit. I'm not really just talking about how I combine the two together, which makes your lives a little bit easier when it comes to running tests. I'll demonstrate that in a bit. And then I'm going to go over some things I found when I was working on doing single phase hardware initialization. And then finally, I'm going to go over some aspects of the documentation that's been updated. There's been a lot of other changes to the code base, just cleaning things up, adding no discard and stuff like that. I talked about that last week, but I just want to say that that's all in at this point. Before there were recommendations by Jason Turner, now they are actually into the code base. Okay. First off, let's go over to unit testing and code process. So now, if you want to run unit tests, you simply just run code create, usually with a period in front to say that I want to create this particular directory, and it'll do a couple of checks. It'll install whatever dependencies we have. Usually, it'll install like if it hasn't installed already, Boost UT, the Boost unit testing framework, and then run your unit tests. And if those pass, then it'll package up and install. So that's pretty much all you have to do to unit test. Before you had to actually there's more steps to this actually. I should probably have written those in. There's a simpler, you'd have to go cd tests, make directory build, cd build, then you would do code create ... That would create that would add those to the well, it really depends on what you needed. This depends on as I said, here's optional depending on what your local dependencies are. And then you run make, and then you run, or cmake, and then you run bin test. I forgot the cmake part here too, which can be kind of long. Oops, daisy. Cmake, insert args here, and it's a bit of a process. Now all that gets taken care of with you for you if you just run code and create, so you don't have to worry about all those other special things. It's just kind of all handled for you. And also simplified the cmake files because now there's just one singular one, and it looks like this. I think I don't have that open yet, so let's click on this. Okay. And here you can see that what we had before was just this section here and this area on top. I added in a force setting of G++ and GCC 11. Usually would never force set your compiler here, but in this particular case, for this particular demo, we're just doing this for unit testing, and this is a hard requirement, so it's not that big a deal. Here we're adding executables, enable for testing, add a test, and so on and so forth. So nothing too crazy here. And then, just adding in the package of Boost UT and then our own package so we can refer to ourselves. That's simply it. Nothing crazier there. And that pretty much does everything we want. And then we have all of our warnings enabled. Probably put more here actually, but actually I think that's a pretty good amount. So yeah, that's pretty much that. Nothing too crazy there. And then, the caveat here is that if you run this, you'll notice that it never actually does incremental builds. So if you do building this way, if you only edited one test file, it would just recompile that one test file and then, run it for you, or, after you build that and then you can run it. With this one, you have to basically build everything over and over again. It's pretty fast on my machine, but might be slower on yours. So that might be an annoyance. But a lot of the tests are pretty simple and pretty quick to build. I believe for CI, our testing system usually takes no more, the full thing, installing everything else like that. I don't think it takes any more than 30 seconds. And I think it's only going to take a couple seconds here. So let me just show you. So if I'm here, I'm not going to use libLPC as an example. It's not the best example. This one works. Let's go with libembeddedhal though. I think that's better. Code in, create. I don't know if I change anything though. Let me boot this up. And there we go. All tests run. 100%. Unit test passed. Everything's good to go. To confirm, to show you guys that it actually is doing something, I'm just going to break the unit test somehow. Let's not do that one. Let's just change this one to the number 4. That'll break. Should compile just fine though. And boom, there you go. You can see all the different tests that have all passed. You can see the one that failed, and we're good to go. So yeah, that's how that works. And if you ever need a unit test, you just simply run code and create, and they'll do it for you. I'm still gonna figure out a way to. You can actually do it the manual way of the cmake file is here. So if you wanted to, you can do a make directory and stuff like that, and then do cmake, and then you have to kind of link some things in, and it gets a little gross. So I'm not the biggest fan of that. But if you want to do it that way, that is a way to do it. I've not written out the instructions for it because I haven't really dug that deep into it yet. But yeah. Okay. So yeah, any questions on that one? Or comments?
So is Conan, because Conan's also the build tool, right? Or is it only for testing?
Yeah, this is only for Conan. If you wanted to develop this thing and run it for, let's say, like just on CMake itself, you'd have to kind of go through the steps. Like this is like a lot of the CMake's kind of formatted in a way that can work on its own, and actually can technically work without Conan. Because if I look back at this, if you look at the actual CMake file, or just go over here to the CMake file, it just requires that you have find package, libembeddedhal, and UT there. But the way that find package works, there's a lot of different ways that find package can basically work. So, but it's supposed to be able to, like, you can set up some things to get it to find certain things. But this is the modern approach for CMake allows things to be as clean as this, but the actual way to make them findable could be very, 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 very varied. So, yeah. But yeah, the main thing is that you're probably going to want to have Conan installed to run all this stuff. Did that answer your question?
Yeah.
Cool. Cool. All right, let's move on to the next one. So next one is single phase hardware initialization, and we're going to talk about all the problems. It's like, are there any problems with initializing hardware and constructors? The answer is yes. This is one of the things I was talking about with Jason Turner, and I told him that the reason why we don't just do everything in the constructor has to do with order of operations. Now, one thing to keep in mind, if I look over here real quick, if I have some code, let me make this C++, and I have like global object A, and then I have global object, or using, or actually, let me make another one. Yeah, let's do two of them. Make someone B, and then using objects C, and it takes A and B. The constructor order will be A, B, and then C, because it kind of has to be that way. These can't be passed into C without A and B being constructed already. So that's actually, for this one compilation, if this is one CPP file, it would work just as intended. No worries here, things are fine. The problem happens when you have things happening in different compilation units. So if you have different files and you combine all together, there's no sense of which one should go first. So it just kind of runs them however the linker kind of got them. The exact ordering really depends on the implementation of the linker. And that's, as far as we're all concerned, it doesn't really matter. It's not something that we should think about. We should just assume that they're all random outside of each individual file. So that's one thing, is that statically and globally allocated objects, the order of their construction is, for single compilation units, defined, but it's undefined across other compilation units, other files that you compile. And that's concerning, because if you have a constructor for your interrupt vector table, or a constructor for your clock system or something like that you globally allocated for some reason, you don't actually know when that particular thing will be allocated, or subset allocated, when it'll be constructed. And you also don't know, let's say you have some other driver that really depends on that particular clock thing in order to work. If it's not already constructed and you assume that it's going to be constructed by the time you run your constructor, that's a problem. But there are ways to get around this. And actually, one of the things that someone would probably say is, like, why don't you just pass in the clock system object into each I2C? And there's actually a way to kind of get around that idea. So I'll go into that actually in the next slide. Next thing is, because of the above issues, if the driver needs a clock driver or interrupt controller to be initialized first, then problems can occur. That's kind of what I was talking about before, is that, like, the problem usually comes up with, like, the interrupt controller and clock driver and the power on controller as well. If those can't exactly run at startup for some reason, then things get a little wonky, and I'll go into how these all work. The problem gets even worse because, and this is something that, like, is a weird kind of finicky thing that I've been kind of pushing. I might just get over it at some point, but I've been trying my best to actually not implement a startup routine for C++. I'm sorry, for C++. Startup routine for the microcontroller, and I'm trying to fall back and just use the CRT0 file. I'm actually going to remove that little section there, because it could be .s, it could be .c, .a, it could be a lot of variety of things. But the main thing about this particular thing, it's called the C runtime initialization sequence, or initialization runtime, or whatever they call it. And it pretty much does the setting up of your stack, setting up of the BSS section, and then after that, running all your constructors. And then after that, then it calls main. And then when you return from main, it will generally just kind of loop. That implementation really depends on what system and target you're planning for. But it's almost every compiler should kind of come with this. ARM comes with it, and it's a very, very minimal startup script. And honestly, it's all you really need. And if you need to initialize the data section, you can do that first thing in main. Right in the start of main, you can initialize your data section there. If you really needed it to be before main gets called, then there's a way to get around that. But I actually have an idea of why you don't actually need that. Okay. So yeah, but another thing is that like if you have a class that depends on the data section being initialized, there could be a runtime or some type of startup script that doesn't actually initialize your data section for you at the right time in which your constructors get run. Let's say someone initializes it afterwards. BSS has to be initialized before you can use almost anything in C, the C standard library. So that has to come first, and will almost always come first. But data, maybe not. So that's where like these kind of problems can come up. So how do we solve these? Oh, and last thing I'll say is that like when I say data section, I mean like a variable that's initialized, that's global. So if you have some int equals 5 somewhere in some global space, you can't guarantee that it's 5 when you are running your constructors. If you need it to be 5, then you are shot out of luck. So how do we fix these problems? A couple ways. So one, we're gonna talk about the data section, and two, we're gonna talk about init order. Init order is actually the more complicated one. For number one, just simply don't write code that needs the data section. If you need data that needs to be initialized, have your constructor initialize it. Have all the things that you need inside your constructor or inside your object. I actually realized that when I re-looked at my code, I used a lot of data section type stuff, and I eliminated it because I realized that I didn't need it. Drivers must basically not depend on any global or static variables that are not set to 0 or can be kept uninitialized. I'm actually going to show you that right now, what that looks like. So if I go over to an LPC implementation, let's go to ADC. I think that's probably one of the easiest ones to look at. We're going to look at specifically how we get the register address. So before what I actually had in the code, I had something like this: inline static reg type ADC, or actually I just called it reg, and I just did reinterpret cast reg type asterisk, and I just put in like something like this. Yeah, something like that. Let's say it's like that. Okay. This is gonna cause a whole variety of problems because it doesn't like that. That's fine. For now, we're just gonna keep it like that. But yeah, this is what it kind of saw before, and it was like, this is gross, doesn't want to do it. I can fix this up. But basically, because I have this inline static meaning that this is not owned by a specific instance of this object. It is owned, it's pretty much a global variable that's just nested inside of the namespace of this thing here. That was a little bit of a confusing terminology for you. It's basically that you can do this ADC, reg, and then, whatever else is inside of it. So you can it's just something that's inside that name. The problem is I had to initialize it to a specific variable. I cannot guarantee that that variable is set when the constructor runs. So how do we get around that? Well, you can have a function, a static function, that its job is basically to return you an instance of that particular, basically a pointer to that register map based on that address. And that just works. And this all kind of dissolves away anyway inside your code with any reasonable optimization level. And it makes it kind of nice as well because you can also throw a constant expression if in here and check to see if it's the right platform. If it's not, you can actually create a dummy variable and return that so your thing doesn't segfault. This is usually meant for unit testing purposes specifically. But that's the utility of this specifically here. And that's how I was able to get rid of one instance of undefined variables is the register variables. Those got all eliminated, which actually saved us space from doing so. So that was cool. And then another place where that happened, or at least I considered it, but I realized I didn't need to worry about it, was here. Here I have a inline static variable. I haven't really initialized these things. It's an array of a set of functions, SID functions. Now, this particular variable here might actually need a constructor. And if it has a constructor, then it actually gets run with the list of other constructors. But the thing is, My constructor does not care about handlers at all. It does not set them with anything. It doesn't do anything special. It just kind of lets them stay. So this thing's completely garbage. That's fine, because the only entries in this handler matrix that would ever get called are ones that have been set up already to basically attach interrupt to them. So if you look at the attach interrupt here, I set up each one of the callbacks based off of what gets sent here, and then the only way these things will ever get called is if I set up an interrupt for rising or falling for that particular pin. So unless something goes really weird and somehow some interrupt triggers for something that wasn't set up already, which is very much so out of bounds when it comes to undefined behavior that at that point we can't really detect it. This particular handler's array is uninitialized, and that's fine. It'll be initialized as we add entries into it, and that's totally fine. So these are two cases of like where we have one case where we have a static inline variable or a global variable where it's actually fine to be uninitialized, and that's fine to stay here. And then we have another case where we had something that was initialized that needed to be defined, and we used a function to kind of get that behavior. So that's that. There's a couple other cases I'll go into in a little bit, and I'll show you them when we get to this section down here. Any questions thus far on this, though, before I go any further? Okay. Solving the init order issue. So basically, I had a bit of a look and think. I had a bit of a think about this, and what really happened here is I really thought about like, okay, well, how do we know that the clocks are set up correctly, or how do we know that the interrupt vector table has already been initialized? We probably don't. It's probably not initialized. But then I realized that all these things that I need are actually things that are very particular to this specific system. That's just to say that it doesn't have to abide by any sort of interface. It's free to do as it needs to. There's no specific behavioral checks it needs to abide by, so you can do whatever you really need to for these things. So I started rewriting them, and I started realizing that like if I have an I2C driver, there are three things that I need to have set up in the system. I need to set up power. I need to power it on. I need to make sure that the interrupt vector table is initialized before I can use it, because I need to put the I2C interrupt handler in the IVT in the interrupt vector table. And then finally, I need to know what the clock settings are. I need to know what they are. I don't need to like change them. I need to know what they are in order to come up with my own clock for my I2C. Now, for power, if we kind of look at this list here, the cool thing about power is that it's just a register. It's just like you give it a number and you tell it, hey, I want this particular peripheral to be powered on. Power just figures out what that number is. Like, okay, this number means this particular register, and then powers that particular register on. That's it. There's nothing really more special than that. So power just really does not even need to worry about initialization. It doesn't care. It can work regardless of the BSS being section set up, whether it is in construction. It can run at any point in time in the code's lifetime. So that actually works without any concern. So we don't have to worry about that. Interrupts. This one's interesting. To initialize the interrupt vector table, you actually use a initialize static function. I was thinking to myself, how do I know that the interrupt vector table has been initialized? Well, there's a register called VTOR, stands for vector. Actually, I'm trying to remember. It's basically the relocation vector for where the the interrupt vector table is. You just specify what the address is in there. There's some other wonky stuff that's in the specifications for it, but that's all I really need to know. Yeah. So this thing is actually set to 0 by default. It's always at reset turned to 0. So we can actually utilize that. We can check to see if the VTOR register is set to 0, and if it is, cool. Then we just initialize it ourselves and relocate it to some RAM located interrupt vector table. If it's not set to 0, that means it's already been set up before, and we can skip that check. I've also added in another function called reinitialize, which will basically, all it does is set the VTOR to 0 and then run initialize again with whatever interrupt vector table length that you specified. And this allows you to, if you needed to reinitialize the interrupt vector table. This is really just meant for unit testing for the most part, but I could imagine for some particular reason, down the line, that becomes a useful thing that we need. So I kept the feature there. I really do hope that no one abuses it and does dumb stuff with it. Like, it's a way to shoot yourself in the foot. Like, somewhere mid-range while the code's already running, it's been running for a while, just running reinitialize at some point, like that would effectively yeet all of the entries in the interrupt vector table, and like things, then chaos would just happen. Usually everything was lock up because interrupt vector handlers would not be able to clear their interrupts, and you get stuck in one of them. But yeah, so that's what happened there. So that's how we solve that problem. We just have some way to check that, whether or not it's been initialized already. Then finally we have clock. Clock can basically use the multi-tin factory pattern to always return a single instance of itself. Now I call it multi-tin because you can actually still make probably other versions of it. Well, at the moment it doesn't do that. It's still kind of singleton esque, but not exactly. I'll actually show you now. So if I look over at the code here, let's look up interrupt. So we can go over to interrupt. Where is initialize? Here we go. So initialize takes a template parameter vector size, calculates it like so, gives a nice good old large alignment, just so that there's a way to calculate this. I could have calculated this, and I think I might even be able to calculate it based off of the vector value here. I just decided that it'd be easier for now to just keep it 512, and we can optimize it later. I had some problems by having it resized to other things. Here we check the system controller object and see if the vector table is something that we don't expect, or if it's no pointer. Is this? If it is, then we simply just run through this list. Set the vector table, and this particular vector table here is a span that is a static inline. It's completely uninitialized, and that's fine because we almost never should use it until we've initialized first. Yeah. So we initialize this to the vector table the static vector table that's here. This is also initialized. We initialize it by filling it up with no-op functions, and then we set.
Quick question.
Yeah, go for it.
I haven't heard of the span standard library object before.
Oh, you haven't? We use it all the time.
Yeah, quick.
Yeah, it's a non-owning array. So you can use it for vector, you can use it for array, you can use it for character array, like if you have a const character array, you can use it for C style arrays. The whole idea is that how if you're gonna pass like a pointer to an array, let's say you have integers to a function, you always have to pass in the length as well. Span is a way to combine those the two parameters into one, and also make constructing it really easy.
Okay.
Yeah. So for example, this is like a standard array here, and I can just assign this directly into a span, and it'll figure out, oh, this is an array. It has, the type is interrupt pointer. It has this many elements. I will then convert that directly into my size and a pointer to that location.
Okay, very cool.
Yeah, super helpful. Super duper helpful. So we fill it up with no ops. A great question, actually, with no ops, and then we set the vector table address to the location of the buffer, and we're pretty much done to go at that point. And anytime you run this initialize over and over and over again, it'll see that this has actually been assigned, and we won't have to worry about this thing running multiple times and clearing out the vector table each time it gets run. So that's how we kind of solve that particular issue here. So this actually allows code like I2C. Let's go down to it. I haven't worked on I2C yet. Let's look at Uart. Where's my constructor? Yeah. So here we have Cortex M interrupt initialize, and then we have this thing called IRQ max. This just converts this enumeration class into an integer or to a value that can just be popped into this thing. And I2C will have the same type of function call. And because they're all using the same value of IRQ max, it'll kind of make the same function call to the same template instance. And they will all check to say, hey, has the thing been initialized? It has been. Cool. We skip until it has been initialized. The first one will be initialized. For all subsequent ones, it will not be initialized. So this is here an example of Uart needs the interrupt vector table. Therefore, it needs to run the interrupt vector table initialize function. And because this thing should exit quickly if it's already been initialized, it shouldn't be that much of a burden when it comes to performance. And also the performance of this thing is pretty small. It's just array, fill with bytes, however number you have, and then go from there. So it's not like it's that big a deal anyway. And then you run the configure function on this particular UART to configure it to what you need for this particular instance. In this case, we go to configure, driver configure. Right, I'm still actually working on this one. Oh, no, I am still working on this one. I need to move some stuff around here, though, because this power on bit thing should not be here, actually. It should be in the constructor. I'm still reformatting some stuff to fit the new scheme. I have gotten to UART. It still works, but just I need to move some things around. Because driver configure should just simply configure the baud rate and the other settings. It shouldn't do the work of resetting the queue, because I don't think, resetting the queue is probably a good idea. Probably flushing the buffer is also a pretty good idea as well. But setting up the receive interrupt should not be done every single time you run the configure. That just doesn't make any sense. Set it up once, and you should be good to go for the rest of the execution for the lifetime of the UART driver. Any questions so far? Cool. Alrighty. So that's the interrupt situation. Now clock. Clock is an interesting one. Clock, if we look over here, where's my clock? Here's my clock. Yeah, so we have internal clock, and then we have get frequency. I think I'm actually trying to change this, actually. Let's look at 80, see if I changed it here. I don't think I have. Let's take a look at clock. I may not have changed this yet. And I have an idea of how to change this in a way that would be fitting. Why are you guys having a problem? Oh my goodness. So I'm still refactoring. I thought that was actually fixed, so that's actually not done yet. Boom. Is that good? Gucci? Yeah, you Gucci. Yeah, so here we have, where's my clock? Where's my clock? Yeah. So it's not been changed yet. So where's my constructor? Come on, constructor, where are you? Should be here. Oh, I deleted him. I did in fact delete him. Got it. That makes sense actually. Yeah, I deleted him because he's not necessary anymore. So what the code actually needs to do at this point is use the get clock function. If you see here, get clock has a static clock object. The static clock object basically just is think of it kind of like a, if you don't know what static means in this context, because I just realized that some people might not actually know this who just joined in. Static means that this particular object is owned, in a way, it's kind of owned by this particular function. It is hidden away from the global space, but it's still somewhat of a global variable. Every time you run this function, that'll be the same clock as the first time you ran it. If I had, like, let's say some type of static, as an example, static int a is equal to 0, and every single time I run it, I increment this and then return that a, this function would return 1, 2, 3, 4, 5, 6, it keep counting up. So that's just kind of something to keep in mind. So every time you run get clock, you get the same clock object. This is important because that means that you will get a clock object that has all of these particular objects set up to their defaults. And when you actually do get clock and then you try to run the reconfigure clocks function, which will basically allow you to change the speed of your CPU and your peripherals and everything else like that to bump it up or even bring it down. That will change the state of that specific object, and you can then see the changes in this object and you can like look at them, you can inspect them and do whatever you need. So this actually needs to be changed out to do get clock. Get clock is the appropriate thing, and that should be like literally a control find, and you can replace all of them and it should just work. And that's another way to get around this whole issue of I have all these different variables that only really exist in a single instance. Like these should only exist by themselves here. There should never be two clock objects where one has a CPU of one value and another has a CPU of a different value. That doesn't really make sense. So to kind of get around that, we have this. But the reason why we still keep this object kind of in singleton form, at least the way I had it before, is that you can create different objects of this and then test them out separately and configure them separately. But at the moment, I think I'm going to probably look into another factory that's specifically for building another clock object. We shall see. This is one of the things that like really lends itself really closely to being a singleton, because there really is only one instance of this object really needing to exist. But yeah, we'll see where this goes. Any questions on how clock kind of bypasses the how kind of gets itself initialized? 。 So yeah, that's pretty much how clock does its thing. You have a little factory function, you get the factory function, get the object from there, and then you call whatever functions you need on it, and you'll just get that same instance of that object's data. Yeah. Any questions on this before we move on to the next section? Just gonna double check, make sure I'm still online. I am still online. Cool.
Yeah, we can hear you fine.
Cool. Alrighty. Finally, let's see, what time is it? Yeah, so 35 minutes in. Documentation has begun. I have been putting an effort into documenting. It's not anywhere near finished at all because there's so much more things that I'm trying to still figure out, but I'm still trying to get some things down before A, I forget them, before B, like it's also kind of make it a little easier for other people to try to contribute. So, if we go over to the README page. Ooh, this is an old one. Did I link the wrong one? What did I say? What? Hold up. Oops, daisy, that's going too far. All right, let's go here. I did link the wrong one. Okay, I'll fix that after this. I'll fix this in post. So here we have libembeddedhal's little area here. Software APIs goes to the old page that we had before. I am actually thinking about ditching this old page. I think it looks really pretty. I think it looks really, really nice, and you have a lot of cool capabilities with it. The only thing is that I've been really kind of digging how how Boost UT has been doing things. So with Boost UT, you can see how everything kind of collapses in, and it's like one short little thing. They have all of that. Look how small the scroll bar is. Look at all that. Now, to you, you might think like, damn, that's so much stuff all in one place. That seems like so excessive. But the thing is, a couple things. One is a navigation bar at the top. So if you need to go to specific areas, you can. And then you can always just kind of pop up back to the top whenever you need to. But also, everything's just kind of there. And if you need to find any documentation for this thing, it's just all in one place. You can just Control F for it and find it. You don't need to like use like a site like this where if I click on this thing here and I do search, I can search for different things, and then let's do ADC here and I see some stuff. Oh, that's kind of cool. There's a little search for me. But here I can just do Control F and find everything. And if I have everything mostly collapsed, you just kind of click on the area that you really need. I might also have a default opened. We'll see how this goes. I'm still trying to format it and clean it up. It's like that. But yeah, no, like let's say you want to know the overview. Click over here, you get the overview of libembeddedhal and why we made it. If you want to look at the motivation, you can see the motivation onto why we made it, like what motivated us to build this thing, as well as some of the design goals we have for it, and some of our inspirations such as Rust's embedded hal. Things you can tweak. So here's a customization file that you can actually modify, and it explains to you in detail how to modify each one of these things. So if you want to like change the platform name, you have to change it through here. If you want to enable stack traces, you can do them here. If you want to increase the stack trace depth from 32 to let's say 8 because you don't think you need to go any deeper than that, that's fine. And also get source position error. If you want to get the position, want to also get like the file name and line number. That stuff's there as well. Coding policies such as style and coding restrictions, things that you can't do in the code. Guides for like how to create a new interface is here. As well as like all guides must follow the C++ core guidelines, which basically for most people here, if you've already gone through the gauntlet of like getting code reviewed by me, you probably are fine for this. I will point out some things and refer back to the C++ core guidelines so that you know what mistakes you're making. But it is a long document, so trying to read through all of it may be a while. But I actually would highly recommend it because it is still really, really good for your own education when it comes to C++. It'll teach you a good amount. Yeah. I also have like an implementation of a peripheral driver and kind of like have it kind of like step by step, but I'm actually going to erase this and I'm going to create a very generic example object rather than using one that already exists because I found that I was starting to hit up against some problems. Yeah, so like I want to have an example pasted here as short as possible, as terse as possible, so that people can go, oh, this is how you take this file, and I implement this file, and little by little I'll be able to just build up my driver as intended for libembeddedhal. Device drivers, I haven't put anything in here, but I'll do that at some point. This one's gonna get pretty nasty or pretty long because there's so many interesting patterns you can use for building device drivers. Specifically, I was talking about this with Nate actually. the PCA I2C to PWM driver. Not only is it a driver that takes in like an I2C and possibly even like, a couple of GPIO, maybe set addresses and stuff like that. Well, not set addresses, but like maybe just hit the interrupt or whatever. There might be some reasons to use the GPIO. I don't think so for that chip though. But it takes I2C. The way that you handle that is a little bit different than how you handle peripherals. Namespacing issues aren't the same. There's a lot of things that aren't the same. But one of the things that you can also do is if you realize that a particular aspect of your driver fits the purpose of another type of interface. For example, there's an I2C to PWM driver. It would make a lot of sense that this particular thing be able to act as a PWM object through the PWM interface. So this thing should have some type of getter saying like, I want to be able to get PWM 0, get PWM 1, get PWM 16, 15. If I go above that, it'll error out. But you should be able to grab instances of that particular PWM object, return those references, and be able to pass those on to other objects that are expecting PWMs. If you're trying to run a whole bunch of servos off that one device, this is a way to do that. Rather than having, So this is a way to make things more modular. So device drivers might get a little long because there's so many different patterns that you can put into doing this to make it so much more modular and then make it so much more easier for things to be moved around. Lastly, a list of libraries. So here's some upcoming libraries I hope to have: NMPU 650, STM, AntMega. I've decided that I do actually want to support AntMega. The code base is actually small enough without exceptions being in there, with just boost leaf, that we can actually probably fit our stuff onto Arduino, and I think that's actually pretty exciting. So I've flip-flopped on this a lot over the years, and I think even now, we're in a good spot to actually do this, implement it, get this code onto Arduinos without all this weird, hacky, special built code and compiler to get things small. I think you can get it small enough and get it on that system for cheap. As a little example, the Uart example that looks over that use the EDC that I have for the LPC right now, the size for that is, I think, 8K. Arduino's AntMega 32.8PU has 32 kilobytes of flash. So you still have and this is like doing like printing to the screen and like, reading off the ADC. Like we still have a good amount of space left to do a lot of other work. And it only uses I think maybe 100 or something, 120 something bytes of, sorry. And this is, I think it's like a good 600 or so, or like 700, 800 so bytes of RAM. The Arduino has 2K. The reason why there's so much RAM usage is because the buffer for the UART is like 512 bytes. So if you just minimize that, you can get smaller. It's all to say that we can support AntMega pretty easily. And then RISC-V as well. And a little area for contributing for later. So yeah, that's kind of what I'm thinking about. I do want to have maybe either fuse the software APIs into the README. That might be a little gross though. But preferably maybe just like have another place where all the doxygen stuff can come up. Because I think the one thing that looks really nice here is this section here, the API. So you just click over on ADC and then see all these different public functions like that. So I think I might just keep something like this here. But I may use something else to kind of visualize it. We'll see how this goes. But yeah, that's pretty much the documentation at the moment. Any questions on the documentation?
I like the one-page layout personally. I think it's a good choice.
Thank you. Nice to get some confirmation. Anything else from anyone else? Cool beans. Before we finish off, I'm actually just going to go over and like kind of talk over. No, I actually think we're good here. Oh, one other thing here that I wanted to bring up. Oh, I did not list this on the slides, and that was a mistake. It's a good thing I actually looked over this. So you'll notice that none of the drivers actually inherit from. We used to do public driver like that. I've eliminated that now. There's no more driver class. This has an obvious impact on the size of each object. The size of objects are now much smaller because they don't contain their settings anymore. And And basically, the paradigm is that every interface should have a configure function if they have something to configure. So for example, for I2C, it has a configure function here, and it takes its own internal settings here. And the only thing that you have to set up is frequency. The other really good example would the other good example actually would be serial, where you have quite a number of settings that you can change for serial settings, and this has its own configure API. One other thing to notice here is that because we're doing single phase initialization, there is literally no need to have a initialize like a settings object that's uninitialized and the one that is initialized to determine what the initialized settings were, because there's no longer a time when this thing isn't initialized. It's always initialized. The moment you construct it is the moment it's initialized. So that gets rid of the other settings. I also realized that, like, honestly, I look back at my old rationale for why we did why we wanted to store the old settings. It was kind of like so you can like look at what things were set up as and maybe query it. And I realized that, like, honestly, the only system that really cares about what the settings are set to is serial. Technically SPI in some weird cases. The only I'll get into that case actually in a sec, but serial, if you pass a Uart or a serial to some object, that other object it knows exactly what type of serial configuration it needs. So it will pass its configuration object settings, into that object, configure it with that. You can never really pass your serial to multiple objects because it's almost always device to device, one device to another device. So it knows what settings it set it to, because either A, the settings were successful and it continued through, or B, it was not successful and you returned out of wherever you were. That's all to say that there's still gonna be some flux with configure, but for now, the thing I wanted to talk about is the fact that, like, ADC no longer has a configure because it doesn't make sense to configure the ADC. ADC just you turn it on, you read bytes out of it. The intricacies of like how fast it samples like that's more of an implementation detail for that specific driver, but it's not on the interface to be able to dictate that, because maybe you have some system that has a fixed frequency of how it samples, so then that configure is going to be useless and a waste of a vtable space. Also last thing to say is that, like, another way to eliminate this is that, like, since we already know what settings you kind of set it to, because the thing that gave the settings knew what those settings were, that also allows you to eliminate having any private variables at all. So now all the interfaces are completely zero size, or zero size. So there's been some RAM savings in how we've redesigned the interface here. So that's kind of neat. Just something to keep in mind if you're ever going to start making your own interface at some point, is that we've gotten rid of the driver class in place of just having a configure and then passing the objects here. And then the hope is that you wouldn't store these. You just simply use them at that state and then ignore the data afterwards. Any questions on configure and how it's being done now? Cool. I'm actually still debating whether or not to even eliminate configure from I2C, or eliminating it from other places for the most part. I think PWM still makes sense to have this frequency here because usually that's something you can configure. Serial, it's very important for it to be able to configure. SPI, I would have said no, you should never need to. But specifically, the SD card implementation requires you to bring the clock rate down to a certain level when it's initializing itself, and then to bring it back up to a higher level. I'm going to relook at the spec again to make sure that's the case, but that's the one case where I think it might be important. Also, a particular driver may need to specify that the clock idle high and data valid on trailing edge needs to be set differently. And if that's the case, then that might actually be a good reason to have configure for the SPI API. But I'm gonna leave them here for now until I figure out that there's a reason to get rid of them. But I think it's solid to keep them at the moment. Any last questions? Cool. All right, I'm gonna stop the recording.